the screen. All right. And so Nicolas Chan is from Berkeley. As we mentioned, this is the Berkeley block, and he's going to be talking about his work with his team on gradient descent over metagrammars for syntax-guided synthesis. Take it away.
Great. Thanks for that introduction. Yeah, so I'm Nicolas Chan. I'm from Berkeley. I'm an undergrad. I just finished my third year, and I'm majoring in computer science and math. And I did this work with Elizabeth Polgreen and Professor Seshia. So today we're going to be talking about gradient descent over metagrammars for syntax-guided synthesis. So first, a quick introduction to syntax-guided synthesis. The goal here is, given a specification, which is a set of logical constraints, we call this sigma, we want to find a function f that satisfies those constraints for all inputs. And in order to do this, to find this function f, we apply a syntactic restriction, which comes in the form of a context-free grammar. So this context-free grammar will contain all the things that you can use in the function. So these might be variables, you can refer to constants, other functions that the function can call. And then the goal here is to synthesize a function f that satisfies your constraints, and we want to also find it quickly. So as I mentioned, in syntax-guided synthesis, we have a grammar that we search through, and this defines a search space for the function f. And the more things you put in your grammar, sorry, the more things you put in the grammar, the larger your search space. So that can potentially slow down your search and make it harder to find the function you're looking for. So if your grammar's too small, then your search space might not be able to express the function you're looking for at all. So there's a balance to be struck between a very large grammar that contains a lot of things that you might not need, and a very small grammar that is not expressive enough to satisfy your constraints. So for example, if you have the function not and a constant true that you're allowed to use, do you need the constant false? It might be that it's beneficial if you're using false a lot, but if you just use it once or not at all, then having not and true might be able to suffice. So in general, our question is, what makes a good grammar for a particular synthesis problem? So that was Sigis and the motivation. And next I'm going to go over our concept of metagrammars, some methods that we use to investigate this, results, and then conclusions in future work. So when you're doing syntax-guided synthesis, since it's syntax-guided, the first thing you have to do is come up with a grammar. So in this example, we have a function f which takes bit vector arguments x and y. And on the left here, we have the rules that we apply to create this grammar for f. So the first rule says add the function arguments. So there's this bitvec non-terminal, and we add the function arguments x and y. So that means that when you're synthesizing this function, it can refer to its own function arguments. Pretty important. You can add other rules. So we have rules 2 and 3, add functions that you can use for bit vectors. So this is bit vector add, which is bit vector addition, and bit vector not, which is bit vector negation. And then you can also have rules that introduce non-terminals for different data types and use those functions. So we have equality, which takes 2 bit vectors and returns a Boolean, and that it's inside the Boolean non-terminal. And then we have if ite is if then else. So this is a simple example for how we can take some rules and turn these into a grammar for a particular synthesis problem. The important thing to note here is, depending on your synthesis problem, you're going to get a different grammar. So if my function f had function arguments x, y, and z, then we would also have z in this grammar, so it would be different. But the rules that we follow would have been the same. So a context-free grammar consists of the terminals and non-terminals that define a set of expressions. And this is what you search through for a particular synthesis problem. This is what was on the right side of the last slide. So we introduced this new idea of a metagrammar, which is the set of rules that define how to construct a grammar for a particular synthesis problem. So on the left is the metagrammar, and on the right is the grammar that is produced by applying this metagrammar to this particular synthesis problem. So a metagrammar is really a function. It takes a benchmark, and it can look at not just the particular attributes of the function, but the entire benchmark. It can look at the benchmark as an input, and then its output is a context-free grammar. So what are some things that might be in the metagrammar? So the metagrammar has a set of rules, and these rules can be very general because you can look at the entire benchmark when coming up with the grammar to insert for your search. So you can create non-terminals for each data type. You can even create differently structured non-terminals. You can populate the non-terminals with argument variables, as we saw before. You can add applicable constants, 0, 1, true or false. Maybe you add different constants too, depending on what you see in the benchmark. You can add functions and or operators for each data type, so plus, minus, things like that, and predicates for different data types. So things like less than or equals to, which returns a Boolean. So the obvious question now is, what rules should we put in our metagrammar in order to get good grammars in general? So to investigate this, we use CVC4, which is one of the state-of-the-art tools for solving syntax-guided synthesis problems. We have to start somewhere. So we used an option in CVC4 where you can trace out how it's constructing a grammar when one's not specified. CVC4 sometimes does other optimizations, such as for single invocation functions, but when it needs to construct a grammar, we try to trace it out to see what it does. And it turns out it creates non-terminals for each data type that's referenced, and then populates these non-terminals with a large set of functions. So we call this the default metagrammar. So the question is, do we really need all these non-terminals and other rules in the metagrammar? Perhaps a smaller metagrammar would help us find the function that we're trying to synthesize faster. So we're going to perform gradient descent over the space of metagrammars in order to see if we can find a more optimal one. So we start with the default, and then we reduce this set by looking at the lower neighbors. So if the metagrammar contains the rules 1 through n, then there will be n lower neighbors of the metagrammar. Then we score these, and I'll get into scoring later. We score these, we find the best one, and then we continue the gradient descent from there. So here's a quick example of how the gradient descent would work. So we have our 4 rules from before, and we start off, we say this is the default, and then we look at the lower neighbors. So this is the default minus 1 rule each. So there's 4 lower neighbors. So those are rules 2, 3, 4, 1 through 4, etc. And then for each of these metagrammars, we use these rules to generate a grammar for each synthesis benchmark file, synthesis problem. And then then we run the synthesis benchmark. And then based on its performance, we can give each metagrammar a score. So in this case, 1, 3, 4 has the best score. So we continue the gradient descent by looking at its lower neighbors. We take rules 3, 4, 1, 4, 1, 3, do the same thing, take these rules for the metagrammar, apply them to the benchmarks to insert a grammar in there, and then give them a score and go with the best one. And we continue down until we have no rules left. Keep in mind that the one at the very bottom is just 1 rule, so it probably won't be expressive enough to solve most of the synthesis problems. So the best metagrammar is actually probably going to be one of the ones in the middle. So probably like 1, 3, 4 or 1, 3. This is simply because a too small grammar is not expressive enough to express satisfy our constraints. All right, so I talked about scoring, and you can't do gradient descent without having some kind of scoring. So scoring is definitely a heuristic, so there can be debate about what the best way to score is. And there's a lot of things you might look for when you're doing syntax guidance. You might look for, I want lots of benchmarks solved really fast, or I just want benchmarks solved at all within my timeout period. I don't care if they take the whole time or 1 second. Or maybe you're looking for quality of results. In our case, we're trying to strike a balance between solving a lot of benchmarks, but also we want to incentivize solving quicker if possible. So for our scoring function, we take standardized performance, so subtract the mean, divide by the standard deviation, compared to the how fast the other metagrammars solve the benchmark. And then we penalize at 10 standard units for not solving. So in our formula, a lower score is the better one. So this is obviously going to be a lot of computational work because you have to generate grammars for each benchmark and then run these benchmarks. So it would be really great if we could train on random subsets. So like a random sample and then generalize to a larger class of benchmarks. So We did this by, we have 3 benchmark classes, and we took a stratified random sample with 48 from class. We actually did this 3 times, and then took the top from each of those 3 runs and run them on the whole set, and the results you'll see today are the best metagrammar from all of those. So the question is, does the reduced grammar found in the training subset generalize to do well on the other benchmarks? And in our case, it did. So here's a table of our results. I'll talk about the enhanced metagrammar later, but the important thing to notice is we do solve some unique benchmarks that we didn't solve before with the reduced metagrammar. And sometimes it's faster. This is a graph. Each dot here is a benchmark, and the y-axis is the time it took the new metagrammar to solve it, and the x-axis is the time it took the default metagrammar to solve it. So anything below the diagonal is an improvement for our reduced metagrammar. And the reason there's a lot of clusters at the 300 is because that's when we timed them out. So we said after 5 minutes, you're done, you didn't solve it. So anything on the right side here is actually a benchmark that wasn't solved before that we solved. All right, so I'm going to do a quick demo. Hopefully you can see my terminal. So this is a hand-picked one that best demonstrates our new metagrammar at its finest. So if we look at this benchmark, this is with the new grammar. There's about 4 rows here. This is the benchmark, and this is the function to be synthesized. And there's the grammar specified here. And there's about 4 rows of things for the bit vector non-terminal. If we look at the original grammar, there's quite a few more. So our new grammar is smaller. So if we run CBC4 using our new grammar, it should solve it fairly quickly. There we go. And then if we run CBC4 using the original grammar, it'll take a lot longer to solve it. In fact, the other one would have probably solved it by now. So you get my point. I'm going to cancel this. And then I'll show you, this is what happens if you don't specify any grammar at all, and you just leave CBC4 up to do it. So at least on this version, it will say unknown. So this is definitely a win in this particular case for our reduced grammar. All right, back to the slides. So I also mentioned earlier that there's an enhanced metagrammar. For this gradient descent, all we do is take away benchmarks or take away rules from the original. But what if we could add some rules that actually improve the solve time? And this is true. So we can add, we tried adding a rule that extracts constants found anywhere in the benchmark and adds these to the grammar for the syntax, for the synthesis function. And this solves 21 new benchmarks that weren't solved before. So you can both take away rules and add rules to the default metagrammar and to find a better one. So to wrap this up, we propose a general framework for coming up with grammars, and this is called Metagrammars. And you can search through the space of metagrammars to find rules that work well to generate good grammars for your synthesis problem. Both adding rules and subtracting rules through gradient descent might give you an improved metagrammar. And we found that in our case, the reduced metagrammars found through gradient descent on the training set can show improvements on the larger set compared to the default. So there's more work to be done here. We should investigate the strategy on more benchmark types. So we mostly focused on bit vectors, but there's a lot more to do. We can explore more rules in the metagrammar, so we can get really creative. These metagrammar rules are implemented as Python functions that just take in the benchmark file. You can look at anything in it. You can make decisions. You can do if statements and stuff, and decide what, if anything, to add to the grammar. We can try different gradient descent search strategies. We only went in one direction. We only reduced the grammar by looking at its lower neighbors. But perhaps instead of removing rules, we add them back. This will increase the computational cost, but maybe we will find a better, more optimal metagrammar. And then we should also look at different solvers besides CPC4 and enumeration orders. So that's it, and I'm happy to take any questions.
All right, let's thank Nicolas. Great job.
Thanks.
There we go. Yeah, press that button again. Excellent. Okay, cool. So we got a few questions here in Slido. Let's go ahead and run through those. We've got a few minutes left. First one at the top from Anonymous. How many constants get added with the add constants rule? Doesn't that risk slowing down risk slowing down the enumeration by adding potentially many more constants?
Mm-hmm. That'll depend on your benchmark. I think maybe he was referring to the enhanced metagrammer. So if you have in the case of the enhanced metagrammer, you're just looking for any constants in the benchmark, and it could slow it down, but usually these constants are useful. Removing some constants, like I mentioned at the very beginning, removing false, if you have not and true, might also help you out. So that it really just depends on if your constant's actually useful in terms of whether it'll slow it down or not.
All right, excellent. Next question. Have you identified any situations where this gradient descent-based approach produces significantly worse results than the default metagrammar?
Yeah. There's definitely a few cases where it does that.
Could you describe a few of those? I'm curious.
So if you take away, if there's some function it relies on that you end up that you end up taking away, then you might not be able to solve the benchmark anymore. So that's why I think the default is just give it as many functions as you can, because that'll make sure that you can definitely express your solution. But if you take so much away that you can't express it, then you have a problem.
All right. Here's a question from Vadim. Would it make sense to formalize your metagrammars properly? For example, with Van Weingard grammars?
I'm not sure what that is, but I think formalization would be useful.
Okay.
Yeah.
Cool. And I think we got a little bit of time for one more. Did you consider exploring metagrammars by metrics other than removing entire rules? You mentioned at the end of the slide, so I guess maybe expand on this. For example, maybe non-terminals in the metagrammars instead of just the entire rules.
So instead of removing entire rules, so the rules there's not a one-to-one mapping between the rules and the non-terminals or terminals. Mm-hmm. One rule could add multiple non-terminals and terminals, so like there was a rule called add predicates, which adds which altogether adds like equals and bitfec unsigned less than and things like that. So these rules can add nothing to the grammar if they don't think they should, or they can add a lot of things. So if you want to do your search in a more fine-grained way, you can make your rules very specific and say each rule will only add one thing.
All right, excellent, cool. So I think that's it on Slido. Let me double check. Yes, it was. All right, so I think that's all the questions. Thank you very much, man. That was a great talk. Talk again.